Welcome to Learn with us. This is the 26th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about field effect transistors. You studied that there are two major classifications of field effect transistors. In your previous lecture, you understood first major classification, which is junction field effect transistors. In your last lecture, you also understood junction field effect transistors, drain characteristic curve, and you also studied about self-biasing of junction field effect transistors. Now, what are the learning objectives of this lecture? In this lecture, you will study about JFET bias point, where you will understand how you are going to establish bias point of junction field effect transistors. In this lecture, you will also understand midpoint bias, and you will also study about voltage divider bias. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is an n-channel JFET. This is Rg for suppose it is 10 mega ohms. Here we have Rs, which is 390 ohms. Here we have Rd, which is 860 ohms. Here we have VDD, and for suppose it is 12 volts, and here this is the direction of drain current, and for suppose it is 8 milliamperes. Here Vg is 0 volts. Again, if you want to find drain to source voltage and gate to source voltage in this case, so how you are going to start your analysis? Again, first we will find source voltage Vs. We know that Vs is equal to IDRs. Here ID is 8 milliamperes, and we know that Rs is 390 ohms. After solving this, you will get 3.12 volts. This is Vs. Now we will find drain voltage Vd. We know that Vd is equal to VDD minus ID Rd. Here VDD is 12 volts and ID is 8 milliamperes, and here Rd is 860 ohms. After solving this, you will get 12 minus 6.88, and here this drain voltage is equal to 5.12 volts. Okay, now we know that drain to source voltage is equal to Vd minus Vs. Here Vd is 5.12 volts and Vs is 3.12 volts. After solving this, you will get 2 volts. So this is your drain to source voltage. Now we will find gate to source voltage. We know that VGS is equal to Vg minus Vs. Here Vg is 0 volts and Vs is 3.12 volts. It means here gate to source voltage is minus 3.12 volts. Okay, this negative value of gate to source voltage indicates that it is n channel JFET. Okay, so this is your answer. Now we will understand bias point of junction field effect transistors. The basic approach to establishing a JFET bias point is to determine the value of drain current for a desired value of gate to source voltage, means VGS, or you have to find the value of gate to source voltage for a desired or given value of drain current. Okay, for this you will use this equation where drain current is approximately equal to IDSS 1 minus gate to source voltage divided by cutoff voltage whole square. It means here this gate to source voltage is not 0, okay, and then you will calculate the value of source resistor Rs, and for this you will use this relationship Rs is equal to gate to source voltage divided by ID, and here you have this. It means you will use absolute values. Now what are these absolute values? Absolute values mean we take the magnitude of a real number without regard to its sign. Okay, so for drain current you will use this relationship, and for source resistor you will use this formula in order to establish bias point of junction field effect transistors. Now look at this example. If you want to find the value of source resistor Rs, which is required to self-bias a JFET when IDSS is 25 milliamperes and cutoff voltage is 15 volts and gate to source voltage is 5 volts. Okay, now first you will find the value of drain current ID. For this you will use this relationship IDSS 1 minus VGS divided by cutoff voltage whole square. Now we put these values here. This is 25 milliamperes and here we have 1 minus 5 volts divided by 15 volts whole square. Okay, now after solving this you will get ID is equal to 11.1 milliamperes. Okay, now for Rs you will use this relationship VGS divided by ID. Okay, now here this VGS is 5 volts and ID is 11.1 milliamperes. Okay, you take their absolute values. Okay, now after solving this you will get 450 ohms. Okay, so this is the value of source resistor which is required to self-bias a junction field effect transistor. Okay, now if you want to find the value of Rs which is required to self-bias a JFET when IDSS is 18 milliamperes, cutoff voltage is 8 volts and gate to source voltage is 4 volts. Now again, first you will find the value of drain current by using this relationship. Okay. Now we'll put the values here. Here we have 18 milliamperes and here we have 1 minus 4 volts divided by 8 volts whole square. Okay, after solving this, you will get drain current is equal to 4.5 milliamperes. Okay, now we will find the value of source resistor using this relationship. Okay, now we know that this gate to source voltage is 4 volts and here we have 4.5 milliamperes. Okay, after solving this, you will get 888.9 ohms. Okay, so this is the value of source resistor which is required to self-bias this junction field effect transistor. Okay, now we will understand midpoint bias of junction field effect transistors. It is usually desirable to bias a junction field effect transistor near the midpoint of its transfer characteristic curve where drain current is equal to IDSS divided by 2. This midpoint bias allows the maximum amount of drain current swing between 0 and IDSS. It means this is the minimum value and this is the maximum value of this drain current. Now we know that the equation of drain current is IDSS 1 minus gate to source voltage divided by cutoff voltage whole square. Now from this equation A, it can be shown that this drain current is approximately 1/2 of this IDSS when gate to source voltage is equal to cutoff voltage divided by 3.4. It means if we put this value of gate to source voltage in equation A, we get IDSS 1 minus cutoff voltage divided by 3.4 divided by cutoff voltage whole square. Now this cutoff voltage will cancel this cutoff voltage. Now we have drain current approximately equal to 1 minus 1 divided by 3.4 whole square, and now we have drain current approximately equal to 1 minus 0.294 whole square, and it is approximately equal to IDSS 0.498. It means it can be written like this: drain current approximately equal to 0.5 IDSS. We know that 0.5 means half. It means here we can say this drain current is approximately 1/2 of IDSS. Okay, when this gate to source voltage is equal to cutoff voltage divided by 3.4. Okay, now to set the drain voltage at midpoint, we use this relation VD is equal to VDD divided by 2, and then we select a value of RD to produce the desired voltage drop. Okay, so this is midpoint bias of junction field effect transistors. Now look at this example. If you have a JFET configuration like this, where the arrow is here, it means it is an N-channel JFET. Here you have source resistor. Here you have gate resistor, for suppose its value is 10 mega ohms, and here we have drain resistor RD, and here we have VDD, for suppose its value is 12 volts here. Okay, now if you want to find the values of drain resistor and source resistor to set up an approximate midpoint bias when the value of IDSS is 1 milliamperes and the value of cutoff voltage is minus 0.5 volts. So how you are going to start your analysis? First we will find the value of drain current ID. We know that for midpoint bias, ID is approximately equal to IDSS divided by 2. It means it is equal to 1 milliamperes divided by 2, which is equal to 0.5 milliamperes. Okay, and again for midpoint bias, we know that gate to source voltage is equal to cutoff voltage divided by 3.4. Here cutoff voltage is minus 0.5 volts, and after solving this you will get minus 147 millivolts. So this is the value of gate to source voltage here. Okay, we know that the formula of source resistor is gate to source voltage divided by drain current, and we take their absolute values. It means here we have 147 millivolts divided by 0.5 milliamperes. After solving this, you will get 294 ohms. Okay, so this is the value of source resistor. Now we will find the value of drain resistor RD. For this we will use this equation. ID is equal to VDD minus VD divided by RD, because we know that ID flows in this direction, and here we have drain voltage VD. for midpoint bias, this VD is equal to VDD divided by 2. Here VDD is 12 volts, it means VD will be 6 volts. Okay, now if we rearrange this equation, we get RD is equal to VDD minus VD divided by ID. Here VDD is 12 volts and VD is 6 volts and ID is 0.5 milliamperes. Okay, so after solving this, you will get RD, which is equal to 12 kilo ohms. Okay, so this is the value of source resistor and this is the value of drain resistor to set up an approximate midpoint bias. Okay, so these are your answers. Now, if you want to find the values of source resistor and drain resistor to set up an approximate midpoint bias when cutoff voltage is minus 2 volts and IDSS is 4 milliamperes. Now again, first you will find the value of drain current. We know that for midpoint bias, drain current is equal to IDSS divided by 2, and here we have 4 milliamperes, and when it is divided by 2 we get 2 milliamperes. Okay, now we know that gate to source voltage is approximately equal to cutoff voltage divided by 3.4. Here this cutoff voltage is minus 2 volts and it is divided by 3.4, and after solving this you will get minus 588 millivolts. Okay, now we will find the value of source resistor Rs. We know that source resistor is equal to gate to source voltage divided by drain current. Here this gate to source voltage is 588 millivolts. We are taking its absolute value and drain current is 2 milliamperes. After solving this, you will get 294 ohms. Okay, now we will find the value of drain resistor RD. Again, we will use this equation. ID is equal to VDD minus VD divided by RD, and if we rearrange this equation, we get VDD minus VD divided by ID. We know that for midpoint bias, VD is equal to VDD divided by 2. Here this VDD is 12, and after dividing it by 2 we get 6 volts. Okay, now we put these values here. VDD is 12 volts, VD is 6 volts and ID is 2 milliamperes. After solving this you will get 3 kilo ohms. Okay, so this is the value of drain resistor and this is the value of source resistor that are required to set up an approximate midpoint bias. Okay, so this is your answer. Now we will understand voltage divider bias. Suppose we have an n-channel JFET with voltage divider bias. Now this configuration will look like this. Okay, the arrow is here. Okay, now this is drain resistor, here we have source resistor, and here we have DC source VDD. Okay, now we are talking about voltage divider bias. It means here we have two gate resistors. This is R1, and here we have R2. Okay, this is gate, so their voltage drop is VG. Here we have Vs, and here we have Vd. Okay, now this is the direction of drain current, and this is the direction of source current. This source is positive here. Okay, now we know that in all field effect transistors, Ig is 0 and Id is equal to Is. Okay, now this source voltage Vs is equal to ISRS. Okay, this is equation number A, and we know that this is Ohm's law. Okay, now we know that this source current is equal to drain current here, so we can write this equation A like this: Vs is equal to IDRS. Now if we want to find the value of this gate voltage here, we will apply voltage divider rule. Okay, now here Vg is equal to R2 divided by R1 plus R2, and it is multiplied by VDD. Okay, in my previous lectures I have mentioned that if we have a configuration like this, then we take the value of that resistor which is close to ground. Okay, that's why we are taking R2 here in this formula. Okay, now we know that gate to source voltage VGS is equal to VG minus Vs. Okay, now from our last slide we know that gate to source voltage is equal to gate voltage minus source voltage. Now for an n channel JFET, this gate to source voltage is negative. It means the voltage at the source, it must be more positive than the voltage at the gate in order to keep the gate source junction reverse biased. Now if we rearrange this equation, we get the equation for source voltage, which will be source voltage is equal to gate voltage minus gate to source voltage. This is equation B. Okay, now from our last slide we know that source voltage is equal to drain current multiplied by source resistor. Now the equation for drain current will be source voltage divided by source resistor. Okay, now here we know that this Vs is Vg minus Vgs. This is equation C. So if we substitute this value here, we get drain current is equal to gate voltage minus gate to source voltage divided by source resistor. Okay, so this is another equation for drain current, and we call this equation D. Okay, Now look at this example. If you have an n-channel JFET voltage divider bias configuration like this, where this source resistor is 2.2 kilo ohms, and here we have drain resistor RD, and for suppose it is 3.3 kilo ohms. Here we have VDD, and for suppose it is 12 volts here, okay, and the arrow is like this. Here we have R1, and for suppose it is 6.8 mega ohms, and here we have R2, which is 1.0 mega ohms. Okay, now if you want to find the values of drain current and gate to source voltage here, okay, and for suppose here VD is approximately equals to 7 volts. So how you are going to start your analysis here? First we will find the value of drain current. Okay, we know that drain current flows in this direction. So the equation of drain current will be VDD minus VD divided by RD, because we know that drain voltage VD is here. Okay, now here this VDD is 12 volts, VD is 7 volts, and we know that RD is 3.3 kilo ohms. Okay, after solving this you will get drain current which is equal to 1.52 milliamperes. Okay, now for gate to source voltage, first we will find the value of source voltage Vs. We know that Vs is equal to drain current multiplied by Rs. Here this drain current is 1.52 milliamperes, and we know that Rs is 2.2 kilo ohms. After solving this you will get 3.34 volts. So this is the value of source voltage here. Now we will find the value of gate voltage, and again for gate voltage we will apply voltage divider rule, and we know that the formula for voltage divider rule is R2 divided by R1 plus R2 multiplied by VDD. Okay, now if we put these values here, here we have 1.0 mega ohms, and R1 plus R2 will be 7.8 mega ohms, and here this VDD is 12 volts. After solving this you will get the value of gate voltage which is 1.54 volts. Okay, now we will find the value of gate to source voltage, which is equal to gate voltage minus source voltage. Here gate voltage is 1.54 volts and source voltage is 3.34 volts. Okay, it means gate to source voltage will be minus 1.8 volts. Okay, the answer is negative because we know that this gate to source voltage is negative for an n channel JFET. It means here this source voltage is more positive as compared to this gate voltage. Okay, so this is your answer. Now here is your class task. Redo analysis of last example given that drain voltage is 6 volts. Okay, that's all for today. Now what are the key takeaways of this lecture? In this lecture you understood how you are going to establish bias point for junction field effect transistors. In this lecture you also understood midpoint bias and voltage divider bias of junction field effect transistors with the help of some examples.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.